Let me introduce you very quickly. So, well, welcome everyone to the afternoon session of the second day of the Quantum Limits of Knowledge Conference 2021. So today we're going to have two talks and then the first roundtable at around 10 past 5 European time. So the first talk is by Antony Valentini. I'm very happy to introduce you, Antony. It's from Augustus College and Clemson University, and it's going to speak about quantum gravity and quantum probability. Antony, as you know, the time for talks is around 45-50 minutes. Do you want me to warn you at some point about time?
Oh, please do. Yeah, that's a good idea.
Great. Okay, you can go whenever you want.
All right. So my subject is quantum gravity and quantum probability. This talk is based on a paper which is just coming out on Archive this week. It's quite a long, detailed paper. In this talk, I'd like to just explain the basic ideas. So there are three main, sorry, I don't see, hang on, okay. There are three main points that I'd like to make. So the first point is the claim, or the first claim is that there is no such thing as the Born rule in quantum gravity. The third, I'll explain exactly what I mean as I go along. The second main point is that the Born rule emerges only in a semi-classical regime where you have an approximately classical space-time background with quantum systems evolving on it. And the third claim is that quantum gravity corrections to the semi-classical regime can make the Born rule actually unstable. So I'll explain a bit more what I mean as I go along. So first thing, the idea that there's no such thing, hang on, I've got something in my eye. Okay, the idea that there's no such thing as the Born rule in quantum gravity. So in quantum gravity, instead of a Schrödinger equation, you have something called the Wheeler-DeWitt equation, in which the wave function is a function or a functional of a three geometry, and there's apparently no time dependence. And the one point I want to make is that the modulus squared of this wave functional is not a probability, which is something that actually people in the field know that there's a problem with interpreting this directly as a probability, but then they do tend to go on and try to find some other candidate for a Born rule or some other way of having a Born-like rule. And my claim is, one of my claims is going to be that this is all wrong. There simply is no Born rule in quantum gravity. The second claims I've mentioned is that the Born rule emerges only in a semi-classical regime. So when you have, for instance, a quantum field evolving on an approximately classical space-time background, you can recover approximately a time-dependent Schrödinger equation, where the time is defined with respect to the background, and you have an effective wave function for quantum system. It could be a quantum field. And when you have a time-dependent Schrödinger equation like this, then the modulus squared of psi can be a probability after a relaxation process has taken place, which I'll explain. The third point, the claim, is that, well, quantum gravity corrections to the semi-classical regime can make the Born rule unstable. What do I mean by that? I mean that if initially I have an ensemble of systems where the probability density is given by psi squared, this can actually evolve away from psi squared. So, for some reason I'm not seeing, hang on. Sorry, I'm not seeing, there's something I need to move here. Whoops, no, hang on. What? Hello?
Yeah, we're here.
Can you still hear me?
Yeah, and also see you now, which is good.
Oh, okay, I got some message saying start my video. Sorry, I just got something that's in the way. Okay, I fixed it now. Apologies, first time I give a talk like this, all feels a bit weird. Okay, so on the first point, which is the point that I'm going to be spending a lot of time on, try to explain why I think there's no such thing as the Born rule in quantum gravity. So the Wheeler-DeWitt equation, as I've said, I'll say a bit more about the equation. This idea that mod psi squared is not a probability. Well, a central point here is that solutions of the Wheeler-DeWitt equation are non-normalizable. Now, there's often been a tendency in the literature to think that, well, this is just some kind of technical issue. Maybe we just need be a bit more sophisticated mathematically. I think actually that's wrong, and that there's a good physical reason for this. That is actually telling us that there is no Born rule in quantum gravity. Now, when I say solutions are non-normalizable, there's a very good reason why they're non-normalizable. And whoops, hang on. And that is because the Wheeler-DeWitt equation mathematically is like a Klein-Gordon equation. Now, those who are not familiar with the Wheeler-DeWitt equation, I mean, to follow this talk, you don't really need any background in quantum gravity. I'm going to explain the essential points, which are quite straightforward. But just for the record, the Wheeler-DeWitt equation looks like this. It's a functional differential equation. The point is that this quantity that appears here, called the DeWitt metric, on superspace. Superspace is just, what it means is a point in superspace defines a 3 geometry, maybe with fields on it. The point is that this metric is indefinite. So here you have a very high dimensional equation, the Wheeler-DeWitt equation, but mathematically it's analogous to a Klein-Gordon equation. Here, imagine I've just got a Klein-Gordon equation for a wave or a single particle wave function, maybe, or something like that, on 4-dimensional space-time. The mass squared term is analogous to this term R that involves the curvature of 3 space. Never mind, the point is that mathematically there's an analogy with the Klein-Gordon equation. Now, what does this imply? What it implies is that if I try to normalize the mod psi squared, if I integrate over the 3 geometries, to try to have that finite, it's analogous to saying, okay, let's take a solution. Imagine I have a solution here, psi, for the Klein-Gordon equation. And I'm going to integrate it not only with respect to x, I'm also going to integrate over t. And I'm going to expect that to somehow be finite. Of course, it's not going to be finite. It's going to diverge. Imagine a wave spreading out in space-time. If I integrate over time as well, it will always diverge. Now, the point is, this is just a mathematical analogy. Here, the space involves the metric degrees of freedom on superspace. Here you've got x and t. The point is that mathematically, if I solve the Wheeler-DeWitt equation, it's analogous to solving the Klein-Gordon equation, and you're going to generate inevitably a solution that is not normalizable. Now, I can illustrate all this with a model from quantum cosmology that doesn't, we don't need to worry so much about all the technical details of the Wheeler-DeWitt equation. So let's look at a simple example. I have an expanding universe, is a homogeneous universe, is expanding with a scale factor A that's a function of time. So that just means that distances get scaled up by this factor A, the universe expanding. And the universe contains a homogeneous matter field with a potential, with some potential. So in the field, in the jargon, this is called a mini superspace model with just 2 degrees of freedom. The scale factor, that is a part of the geometry, that's the geometrical part of the geometry of space. And I've got a field, a homogeneous matter field. Okay, what does the Wheeler-DeWitt equation look like? I have a Wheeler-DeWitt equation it's just a function of these 2 degrees of freedom. There's a rescaled Planck mass that appears in here. This is what it looks like. Okay, this is what, the result of quantizing this system according to the usual rules. This is what you get. Now, what we can do is we can just rewrite this a bit. If I introduce a variable alpha, that's the log of the scale factor, I can put the equation in this form. It is just, it is now literally exactly a 2-dimensional Klein-Gordon equation with a potential term. So now let's just think about this equation here. Here we're looking at a simple model of quantum gravity or quantum cosmology. I have a wave equation with the potential term. If I just ignore the potential for a moment, we all know that the free part of this equation has a general solution like this, just packets traveling at a wave speed, which here is the Planck mass in this mini superspace. Obviously, these solutions are not going to be normalizable. Okay, so I hope this is just by way of explaining where this non-normalizability of the Wheeler-DeWitt wave functional comes from. It's the Klein-Gordon-like structure of the Wheeler-DeWitt equation. So moral of this is that, well, okay, if you can't normalize psi, and it's not just some technical issue that maybe I can get rid of by discretizing or something. No. This is actually the wave that is spreading. There's a wave-like propagation, as it were, in configuration space. So clearly, this is the idea that this is normalizable is for the birds. So the idea that this is a probability is naive. Now, so far, I haven't said anything that people in quantum gravity circles don't know. This is well known in quantum gravity circles. There's some very good reviews of the problem of time in quantum gravity. There's a huge book by Anderson that came out 4 years ago. This is called, to treat this as a probability in the field, it's called the naive Schrödinger interpretation. It was Unruh and Wald who first called it naive. This interpretation had actually been applied extensively by Hawking and collaborators in the 80s, but it doesn't really work. It doesn't really make sense. One issue is that there's a timeless, sorry, I've actually added here in the wave function, I've included a matter field. I've got the metric and a matter field as well. So, this probability is timeless. So there are issues about, well, how do you interpret this? How do you apply it? There's a lot of literature on trying to make sense of this, but ultimately it fails because this thing is just not normalizable. Okay, so the naive Schrödinger interpret. I should mention, if you look, for instance, this book by Anderson, it's over 900 pages. He looks at dozens of different approaches to the problem of time in quantum gravity. There isn't really a consensus in the field, but there is a consensus that this interpretation is naive. I mean, I think there's one thing that everyone agrees on, that this is really no good. Okay, so now why is this naive? There's a common we've said that, well, it's because psi is not normalizable, and we've said that it's because of the Klein-Gordon-like character of the Wheeler-DeWitt equation. There's another way of looking at this, is quite common, is to say that this probability, to call this a probability, is naive because time is actually hidden in the 3 metric. So what do I mean? So for example, in quantum cosmology, if I have a wave functional, I've got the scale factor and a scalar field. Well, the idea is, one idea is that you could treat the scale factor as time. There is no time, but the actual size of the universe itself can act as a sort of clock. Now, there's a long history of this. It is controversial. There are issues about, do you recover standard quantum mechanics? What happens, for example, if this to time, if, for example, the universe expands and then recontracts, does time stop and start going backwards? What happens? Now, a view I think that some people take, that I think DeWitt took, and I think Rovelli takes, is that, well, in this theory, the idea of time is just not fundamental. It emerges only approximately in certain conditions. So if you find situations such as this, where our notion of time seems to run into trouble, well, that's just because our notion of time is limited. So there's one way of looking at it. But I think it's worth saying that all these issues are controversial. People wouldn't be publishing 900-page books on the problem of time if the matter was settled. So, okay, I'd like to propose a new explanation for why this probability is naive. Okay, the new explanation is that in the deep quantum gravity regime at the Planck scale, where you really need the full quantum gravity with the Wheeler-DeWitt equation, there simply is no such thing as the Born rule. We're used to looking at systems on a classical space-time background with the time-dependent wave function, the mod psi squared of the wave function. It gives you probabilities. We're used to this, and I think the claim is that we're making a mistake when we try to apply the same idea to the deep quantum gravity regime. Now, as I'll talk about in a bit more detail, we can talk about probabilities, and we can have them evolving in time, but they're not tied to the Born rule. In fact, the claim I'm going to make is not just that they're not tied to the Born rule, but necessarily probabilities in the deep quantum gravity regime cannot equal mod psi squared ever. You always have p not equal to psi squared, always. So in a sense, quantum gravity is in a perpetual state of non-equilibrium. Perhaps more accurately, hang on, again, I can't see my, okay, and I'm saying that this is the true physical significance of this non-normalizability, that quantum gravity is in a sense, in a perpetual state of non-equilibrium. Now, to make sense of this, of course, normally in quantum physics, you can't even contemplate probabilities that are not equal to psi squared. So you may be thinking, what on earth is he talking about? So we need a formulation of quantum mechanics in which probabilities are not necessarily tied to psi squared. And one such formulation is the pilot wave theory of de Broglie and Bohm, at least when interpreted correctly. I mean, in my view, a lot of people interpret it incorrectly, but there you are. So the way I look at this is that in de Broglie-Bohm pilot wave theory, the Born rule is not an axiom or law. It corresponds to a state of statistical equilibrium that's analogous to classical thermal equilibrium. And I've been banging on about this for a long time now. The first paper appeared in 1991. Let me give a quick, because I've got a lot of other things to say, let me just very quickly whiz over this is sort of bit of background, how I look at the Born rule in pilot wave theory. So quick thumbnail sketch of pilot wave theory. We've got the usual, so here I'm just talking about non-gravitational physics. I have a classical space-time background. I have a quantum system with a wave function psi, a usual Schrödinger equation. In pilot wave theory, there's an actual configuration evolving with time, according to de Broglie's equation of motion, which for standard systems, this turns out to be proportional to the gradient of the phase of the wave function. Now, if we assume that I actually have trajectories following this velocity field, then by construction, if I have an ensemble of systems with the same wave function, by construction, the probability density will follow this continuity equation. This just says that that each configuration is moving with this velocity. And this is true regardless of what rho is, even if rho is not equal to psi squared, okay? Rho will evolve by this equation. Now, it happens to be that this is the same equation that's satisfied by psi squared. From the Schrödinger equation, I can derive this continuity equation for psi squared. It has the same velocity field in it, proportional to the gradient of phase. So I have a simple theorem that this density, if rho is initially psi squared, then it will remain psi squared. So you have a sort of equilibrium theorem. If you happen to have rho is psi squared, you stay there. But and at this point, most people in the field take this as an axiom, that it's just one of the laws. I think Holland in his book lists 3 laws of pilot wave theory. You've got the Schrödinger equation, you've got a guidance equation, and you've got this law. And Duhr, Goldstein, Zangi, Tumulka, various people, they tend to think of this as somehow built into the structure of the theory. I think that's wrong. But we can ask, why do we find, so at some initial time in the lab, why do we find rho is psi squared? It's true, if I set up an ensemble of systems in the lab, I prepare it with the wave function psi, I always find this distribution. Why, if it's not a law, why do we always see it? My claim, when I've talked about this a lot for a long time, so I'm going to go very quick here, is that the explanation is because of quantum relaxation in the remote past, that you can start outside here with a distribution with probabilities not psi squared, and under reasonable conditions, the equations will make you relax into this region that we're stuck in, where we see these probabilities. So this kind of thing, here I'm showing the results of a numerical simulation for particles in a 2-dimensional box. Here's the wave function squared evolving with time. We start off with a density rho that is not psi squared. We let it evolve. and lo and behold, pretty quickly and quite accurately, it approaches psi squared. This can be quantified with a coarse-grained H function, which is quite useful. It's basically minus the relative entropy of the coarse-grained density rho with respect to the coarse-grained psi squared. This obeys an H theorem, which is analogous to the classical coarse-graining H theorem, assuming no initial fine-grained structure in the densities. Numerical simulations show an approximately exponential decay of the coarse-grained H function. Here's log H, or coarse-grained H, log H against T. This has been confirmed by many independent situations. Here's an example of a 2D oscillator. Here time is going downwards. Here's the initial psi squared. I have 25 modes in superposition. So this is just the Schrödinger evolution of psi squared. Here I start with a Gaussian rho that's not equal to psi squared. I let it evolve, and you see it quickly approaches equilibrium. Here's a plot of coarse-grained H against T. You see the exponential decay. Okay, so here's an idea. When did quantum relaxation happen? So I've argued at length that this presumably happened a long time ago in the very early universe. All the systems that we have access to have a long and violent history. So it makes sense that this process will have happened a long time ago, soon after the Big Bang, potentially testable in the CMB. I've done a lot of work on that in the last 10 years. Let me move on, okay? So let's just take this idea that non-gravitational pilot wave theory, the Born rule is not a law of nature. It holds only because we're stuck in equilibrium. And we're trapped in a stable quantum equilibrium. Once, in a sense, there's a sort of depressing bad news about this point of view, is because once rho is psi squared is reached, we stay there with no hope of escape, barring extremely rare fluctuations. So it's like standing next to the oceans and waiting for it to start boiling. Not a very good prospect. Okay, so at least this is what we find in non-gravitational physics. Once you reach this quantum equilibrium state, you're stuck there. The claim I'm making in this talk is that things are very different in quantum gravity. So let's look at pilot wave quantum gravity. There's some pioneering papers here. Vink, Horiguchi, Shtanov, and Pinto-Neto and his collaborators have done a lot of work on this in pilot wave quantum cosmology. Has a nice review paper here. Pilot wave quantum gravity basically says, look, here's the Wheeler-DeWitt equation. There's also a constraint, a momentum constraint on psi, which I'm not the people who know about these things will know about that. Never mind. I have a wave functional of the three metric here. I'm just going to ignore any matter fields for the moment. I've got the wave equation. It's like the Schrödinger equation, but it's not like the Schrödinger equation. And I add a guidance equation that tells me what is the time derivative of the three metric. And never mind about these factors. The point is it's proportional to the sort of generalized gradient of the phase in superspace, okay? Now, this defines the dynamics of a single system. There are potentially some issues with this, which we might talk about in the questions, but let's just take it that this defines the dynamics of a three geometry evolving in time. Question remains, how can we construct the theory of a quantum equilibrium ensemble, remembering that psi is not normalizable? So my claim is the following, that look, you can write down the theory for a general ensemble, where an arbitrary ensemble with a distribution P will evolve by a continuity equation, which just says that, well, each element of the ensemble is evolving according to the guidance equation. But the claim is that this theory has no equilibrium state. Now, instead of looking at this quite technical formalism here, let's look at our simple quantum cosmological model. Okay, illustrate with a model of quantum cosmology. Here, remember, we've got the scale factor, we've got a homogeneous scalar field. This is what the Wheeler-DeWitt equation looks like. Let's look at this in de Broglie pilot wave theory. Well, if I do if I insert this polar decomposition into here and take real and imaginary parts, The imaginary part the real part gives you a modified Hamilton-Jacobi equation. The imaginary part gives you this, what I call a pseudo continuity equation. I say pseudo because the density is not normalizable, but it looks like a continuity equation. Remember that psi squared doesn't depend on time, so there's no d by dt term here. So if you look at this, someone who's used to de Broglie theory will say, right, what we have is a density, a squared psi squared, and de Broglie velocities, which again are proportional to the gradient of the phase with some factors here. The fact that there's an a squared in front of psi squared, there's no great significance to that. It's still a Born-like rule. It's just the way the volume element works in this mini superspace. So there's an a squared factor. Now, the point is, if we now accept, all right, we've written down the de Broglie theory of this. We've got the wave equation. We have de Broglie velocities for the actual scale factors evolving in time. This homogeneous field is evolving in time. These are the equations for the trajectories. If I now look at an ensemble, a theoretical ensemble with the same wave function, a general probability density by construction must evolve according to this continuity equation. Okay. So now, at this point, we must be aware of the naive Schrödinger interpretation, which has reared its head again in pilot wave theory. So there's a recent paper by Doran Struve, also the pioneering paper by Vink, I think makes this mistake, is that you might think the following. I mean, in a way, it's an understandable mistake, but I think it is still a serious mistake, that since P and a squared psi squared obey the same equations. Now remember, there's no t in psi, so I could have a d by dt psi squared here. It just happens to be 0. These are the same equations, the same continuity equations. You might think, well, again, I have a state of quantum equilibrium. If p is equal to a squared psi squared initially, because these two quantities obey the same continuity equation, if they're equal initially, they will remain equal. I have quantum equilibrium. What's not to like? Well, the problem is that this, the left-hand side P is normalizable by construction. It's a probability density. The right-hand side is not normalizable, and this can't be fixed by any of the usual tricks. In fact, I would say that I claim the following, that we must have P not equal to a squared psi squared always. Formally, we can look at this in terms of a coarse-grained H function. The H theorem still goes through, even though psi is not normalizable, but the coarse-grained H function has no lower bound. It's usually bounded below by 0. So this means that if I'm hoping, it might P relax towards this Born-like density, well, equilibrium can never be reached. So as I've said, heuristically, quantum gravity is in perpetual non-equilibrium. That perhaps more precisely to say is that there simply is no equilibrium state. Okay, time is pressing. Let me move on now with some. So I think, I've spent a lot of time on this first claim, that there's no such thing as quantum equilibrium or the Born rule in quantum gravity. We simply have to accept that we have general probability distributions. There's no such thing as a quantum equilibrium state. We have to forget all that in the deep quantum gravity regime. Some implications, and here I'm going to have to speed up briefly. So the second claim is that the Born rule emerges only in a semi-classical regime. So the claim is that when I have an approximately classical space-time background, you recover time-dependent Schrödinger equation with normalizable wave functions for quantum fields or whatever quantum systems you have. And then psi squared can be a probability after relaxation has taken place. Now, how does this work? So let me give you the gist of it. Semi-classical approximation is something that's well studied in quantum gravity circles. So what you do is you take a solution to the Wheeler-DeWitt equation of this form. You have a WKB solution for just the geometry, which basically means the geometry is approximately classical. And this is multiplied by a wave function that depends on the quantum field that you're interested in, but also depends on the background geometry. And the idea is that, well, in this approximation, the background geometry is behaving approximately classically. Now, the usual way this is done is often using something called WKB time. And, you know, they sort of surreptitiously put in trajectories for the 3 geometry associated with this WKB wave function. What they're actually doing is de Broglie-Bohm theory for the special case of this WKB wave function. But let me just say what the result is that you obtain an effective time-dependent wave function for the quantum field. And this is standard stuff in the quantum gravity literature. You get an effective time-dependent wave function, which looks like this. I've got to remember there's no t in here, but what happens, the 3 metric is now following a classical trajectory that depends on time. So you've got an implicit time dependence, which I can reinterpret as an explicit time dependence. It's basically because psi depends on a 3 metric that depends on time, psi ends up depending on time. So I get effectively a time-dependent wave function, and you can get an effective Schrödinger equation. So, for example, a nice paper by Kiefer and Singh in the early 90s showing how you get an effective Schrödinger equation for this might be, for instance, a quantum field evolving on an approximately classical space-time background. So now, why is this important for us? Is that, well, once you have an effective Schrödinger equation, then in de Broglie-Bohm theory, conventional quantum relaxation can take place. So as we emerge from the deep quantum gravity regime into the semi-classical regime, then I remember I've said that in the deep quantum gravity regime, there's no equilibrium state. The coarse-grained H function has no lower bound. You can never reach equilibrium. But once you're in this regime, then conventional relaxation can take place. There's something else that's important, is that note, because fundamentally in the underlying quantum gravity regime, probabilities can never be equal to psi squared. As we enter the Schrödinger regime, the initial conditional density for this quantum field on the classical background, this is just conditional probability here, will be not equal to the modulus squared of the effective emergent wave function. In other words, as you emerge from the deep quantum gravity regime and you enter the Schrödinger regime, you'll be out of equilibrium. Your quantum field on this approximately classical space-time background is expected to be out of equilibrium. This is, so the semi-classical universe begins out of equilibrium and relaxes to the Born rule only afterwards. Now, if I could maybe just, as a good point to just ponder for a moment, this claim here that the semi-classical universe will begin out of equilibrium, relaxes to the Born rule only afterwards. This is a hypothesis that I made back in 1991, and my claim now is that this hypothesis that the universe after the quantum gravity regime is in a state of primordial non-equilibrium, I claim is actually a consequence of quantum gravity, at least in terms of de Broglie-Bohm. Moving on, one more thing. And I think I have about 7 minutes.
No, actually, you have 13 because we started.
Oh, brilliant. Okay, brilliant. Okay, good, fantastic. Okay, so one more thing. Okay, so let me just maybe recap what I've said. So the 2 main points I've covered so far is that in the deep quantum gravity regime, there's no such thing as the Born rule. There's no such thing as quantum equilibrium. As you emerge into the semi-classical regime, initially you will be out of equilibrium, but because the effective Schrödinger equation, you now have an effective time-dependent Schrödinger equation, you recover the usual kind of time-dependent wave function we used to, then you can get quantum relaxation, and studies have been done numerically too of quantum relaxation on expanding space, for quantum field on expanding space. Done a lot of work on this with Samuel Colin the last 7-8 years. You get the usual kind of relaxation, at least at wavelengths that are small compared to the Hubble length. But anyway, it's something we could talk about. But there we go. So that's the picture so far. So it looks as if, even though, so it's interesting that there's a claim here But fundamentally in quantum gravity, there's no Born rule. And you might think, well, then how on earth are we going to explain the fact that we see the Born rule in everyday systems in the lab? Well, the explanation is that when you enter the semi-classical regime with the classical space-time background, then you get relaxation to the Born rule. And that explains why we see what we see. Okay, so we're back to being stuck in quantum equilibrium. We've got rho is psi squared. But now there's something interesting happens, is that there are quantum gravity corrections to the semi-classical regime. And my third claim is that these can make the Born rule unstable. So what we're looking at is, if you like, an intermediate regime in which you've got a time-dependent Schrödinger equation, but it has quantum gravitational corrections. Now, such corrections have been studied over the last 30 years by Kiefer and Singh and Kiefer with a number of other collaborators, including right up until the last 4 or 5 years. What they find is that while you recover an effective time-dependent Schrödinger equation, but there are small corrections to the effective Hamiltonian that come from quantum gravity. Some of these corrections are non-Hermitian. Now, in standard quantum mechanics, that violates probability conservation, and Kiefer and collaborators, they tend to, they're not quite sure what to do with this, and they tend to ignore these terms and feel, well, how do you handle them? But in pilot wave theory, if you look at this in pilot wave theory, probability is conserved. And what happens when you have a non-Hermitian term in the Hamiltonian, all that happens is that the Born rule becomes unstable. Now, seeing as I do have a few minutes, let me show you how that works. Can you still hear me? Hello?
Yeah.
Okay, so here's what happens. So, for example, some papers, 2012, 2013, this again, Kiefer and collaborators, were looking at mini superspace models, deriving an effective wave function for a matter field. What you find is a Schrödinger-like equation. Here is your usual Hamiltonian for the matter field. So normally these two terms would not be here. Here, these two terms are small quantum gravitational corrections. The first term is Hermitian. The second term is non-Hermitian. Now, what Kiefer and co tend to do is they ignore the non-Hermitian term, and they've looked at the Hermitian term, and they've calculated, for example, how it changes the fluctuations for the inflaton field during inflation. You get a small change in the CMB spectrum, small effects at large scales, and they've done quite a lot of work on this. But this non-Hermitian term, well, it's there in the background, but they tend to ignore it because they're not quite sure what to do with it. In pilot wave theory, there is no problem. Let's look quickly at pilot wave theory with a non-Hermitian Hamiltonian. Let's imagine I have a Schrödinger equation. Here, H1 and H2 are Hermitian. If you look at the continuity equation for psi squared, you find that it's no longer, psi squared is no longer conserved. There's a source term. Here, J1 is the standard current proportional to the gradient of phase that's associated with the Hermitian part. What does this imply? So the norm of psi squared, as you would expect, is no longer constant in time. And I keep not being able to see what, okay. Now, what happens is, so here, this effective, sorry, can you still hear me? Hello? Yes, good. So this effective Schrödinger equation, this emerges from the semi-classical regime in quantum gravity with these non-Hermitian corrections. The papers by Kiefer and co, they go into a lot of detail of showing how this equation arises. And I've gone through it carefully, and I've managed to show that if you look at the de Broglie velocity field for the quantum field, you find that the de Broglie velocity field suffers no correction. It's just the velocity field that is associated with the Hermitian part. So let me just repeat that, because this is important. The quantum gravitational corrections derived by Kiefer and co, the Schrödinger equation has these corrections, and there's this peculiar non-Hermitian term. The de Broglie velocity field is unchanged. at least to the order that they calculate. What does this mean? This means that the density rho satisfies the usual continuity equation with the usual velocity field, whereas, as I've said, the psi squared has this source term. So the claim here is that quantum gravity implies in this approximation a pilot wave theory with an unstable Born rule, because the density rho obeys the usual continuity equation, whereas psi squared, there's a source, obeys the same equation here, the same velocity field, but with a source term. So the ratio of rho to psi squared is no longer conserved. So we have, as a consequence of quantum gravity, I'm claiming, in the effective semiclassical regime with these corrections, you derive a pilot wave theory with an unstable Born rule. If initially rho is psi squared, then generally rho is not psi squared later, and you can estimate the time scale over which this process occurs. Let me give you an example, and I've almost finished. I think I've just 2 more slides, so I just have another 2 or 3 minutes, and I'll finish. Let me give you an example of what Kiefer and et al. Find. So here's a paper from 2016. They're looking at an effective Schrödinger equation for scalar perturbations on de Sitter space. And they find a corrected Schrödinger equation. So imagine this is the wave function for a field mode. So I've got a scalar field. Imagine I'm looking at the components in Fourier space. And this is the wave function for one of the modes. And this Hamiltonian is just the usual Hamiltonian for a field mode. So this here would be the usual Schrödinger equation that you would expect for say for the mode of a free scalar field on a de Sitter de Sitter background is just an exponentially expanding space. Now here are the quantum gravitational corrections. Here there's a Planck mass appearing. There's a Hermitian term that's proportional to the square of the usual Hamiltonian, and there's an I here. So there's a non-Hermitian term that involves the time derivative of the usual Hamiltonian. The scale factor is in here. This is the non-Hermitian term, which Kiefer and co are unable to interpret, but which in pilot wave theory is perfectly straightforward. There is no difficulty with having such a term. And in fact, in this paper, which is just should be out on publicly available in a couple of days, I've used this equation to calculate the creation of quantum non-equilibrium during inflation. And I find that there's a small power deficit, which is actually not probably, it's going to be too small to be observable. But it sort of adds, Kiefer and co, what they do is they use the Hermitian term to calculate corrections to the Schrödinger wave function, and they find corrections to the power spectrum. Here there are additional corrections which from this term, which I'm able to calculate in this way from pilot wave theory. Brief mention, similar effects for evaporating black holes. If you look at the original paper of Kiefer and Singh in 1991, you find that in general, there is a non-Hermitian term, a correction term to the effective Schrödinger equation, which looks a bit like this. It depends. It's a time derivative of the Hamiltonian, and in a time-dependent situation such as an evaporating black hole, this term will be there. And in fact, Kiefer himself considered this term. There's a paper he has in the mid-90s where he was wondering if this term might help with the problem of black hole information loss. I'm not sure that his proposal, there is this problem that if you're in standard quantum mechanics, well, such a term doesn't really make sense. But I've looked at this again in pilot wave theory, and what this term does is it simply tells you that during black hole evaporation, the quantum field evolving on this background spacetime will evolve away from the Born rule. However, the estimates that I've done show that this effect becomes important only as the mass approaches the Planck mass. The hole is evaporating away right at the very last stage. It looks as if this effect could become significant. So my last slide, my conclusions, is that, well, first, as I've said, quantum gravity is fundamentally a quantum non-equilibrium theory. There's no Born rule. An equilibrium state exists only once we enter the semi-classical regime with time-dependent and normalizable wave functions. At the start of the semi-classical regime, when you look at the conditional probability for your quantum system, you will find initial non-equilibrium, which can then relax in the usual way to yield the usual Born rule. However, corrections to the semi-classical regime can yield a small instability in which non-equilibrium can be created. These latter effects are very small, but perhaps significant for evaporating primordial black holes, which are considered in various astrophysical scenarios as potentially observable, as potential candidates for dark matter and so on. There's another story. And that's it. I finished. There we are. Thank you. Should I now stop screen sharing, or?
I think you can, yeah, I can stop sharing and then it's
I'll stop sharing. So now I can see you, right? Okay.
Thanks for the talk. Amazing.
Well, thank you.
And perfectly on time also.
Brilliant, brilliant.
So now we have around 22, 23 minutes Q&A so that we can have a break. As usual, as we are doing the last 2 days, please write your name on the chat. Also, if you have a finger. Okay, already see a question from Aurelian. You can go first.
Okay, thank you. Thank you very much for your very interesting.
Hello there.
Hello.
So we've never met. Apologies, I did not reply to your email. I've just been too busy, but I'll get to it.
Very not a problem. Very not a problem.
Nice to meet you.
Yeah, me too. So very great talk, and thank you very much for presenting something like that. And I have two questions which are related, and the first one is about the meaning of the probabilities distribution for universe, because if you have I can understand that I think I share more or less the same view than you concerning the status of probability in Bohmian mechanics or the Broglie theory. So you need copies of ensembles somehow, copy of systems in order to make sense of a probability. You need to have a distribution of systems. So I imagine that to make sense of a probability distribution of universe, you mean many copies of the universe, like a multiverse somehow. Otherwise, if you have only one single universe, then the distribution will be a Dirac peak in. All
right. So look, this is a fair question, and it often comes up. Now, I mean, a few things to say on that. Is it cosmologists? And I'm really thinking of observational cosmologists. For instance, people looking at the CMB. They work with this sort of thing all the time. So we have one CMB sky, and yet people talk about statistics for the CMB sky. We have one universe with galaxies distributed in space, and yet there are large-scale structure surveys that talk about distributions of galaxies, looking for non-Gaussianity, this, that, and the other. And this has been going on for decades, and hundreds of millions of dollars are spent on these projects. So what are they doing? So here's one way to think about it. Well, actually, I mean, there are several ways to think about it. One way is to think that, well, the universe has a kind of statistical homogeneity on very large scales. So, I can think of a large number. I can take a big region. It's not the whole universe, but it's big enough. And the universe consists of many such regions. And then I have a kind of effective actual ensemble. Okay? That's one way to think about it. Another way to think about it, which is what I tend to do, is well, let's let's imagine that we have a theoretical ensemble, and a theoretical ensemble of universes, and let's assume that the probability distribution for the theoretical ensemble is translationally invariant and also rotationally invariant. What you then find, I mean, I've discussed this in detail in a paper a year or two ago about the status of the Born rule in the Broglie-Bohm. There's a section about this. If you look at what cosmologists do, I mean, let me be specific. Let's say a concrete example of the microwave sky. You've got one temperature distribution on the sky that's slightly anisotropic. I can expand that in spherical harmonics to get some coefficients that describe this function. Cosmologists talk about statistics for these coefficients. Well, what are they doing? Well, what happens is, if you assume that the temperature that we see is a realization that was drawn from an underlying ensemble that is statistically isotropic, what you can show is that the coefficients in this spherical harmonic expansion that depend on L and M, as in usual spherical harmonic expansion, is that the theoretical ensemble average, or the variance for these coefficients does not depend on M. It depends only on L.
Yeah.
So what that means is, if L is not too small for a given spherical harmonic what's the term, multipole L, I've got 2L plus 1 coefficients that all have the same variance. So if L is large, I actually can start talking about statistics for these things, and I can actually probe the underlying theoretical ensemble. That's how it works. There's also an assumption of statistical homogeneity that comes in when you talk about this. I mean, if you want, I've gone through this carefully. I mean, I wrote a paper partly to address this kind of thing. I mean, the papers and the books in cosmology, I think they tend not to explain this very well. I mean, the cosmologists I've spoken to, I think they know what they're doing, but they're just somehow, this thing is just, people have just accepted these ideas, but it's not really laid out in detail exactly how it works. But basically, the short version is that by assuming that the underlying theoretical ensemble is statistically homogeneous and isotropic, you can relate measurements on a single universe to you can probe the underlying theoretical ensemble, surprising as it may seem. But so I don't think there's really a problem. I mean, look, and as I say, people are making observations of the distributions of galaxies and of the anisotropies in the CMB, and they managed to rule out certain theories of inflation that predict a spectrum that it turns out to be wrong. I mean, they are ruling out a certain prediction for the probability distribution.
Makes sense.
So sorry, it's a bit of a long answer, but
no, but it was fine.
Okay.
So was my question, but I have another question, but it depends if other people's. I don't know, Cristian, if you have...
So for now, I don't have people in the list, so you can go on.
A second one, which was related, it was about the fact that the origin of the time dependence in the probability density is very interesting, because I have the feeling that when you watch the Wheeler-DeWitt equation, one of the motivations for telling that there is no time already in this Hamiltonian equation is that there is a diffeomorphism invariance, so it's looking like it's the general relativity principle somehow. So now, in new density of probability, the more general formula for density of probability, you include the term which is the time derivative of rho and of probability density. Then it means that maybe you are allowing some breaking of this symmetry. I'm not sure. I'm not specialist of this topic. So
yes. Well, what happens is that normally when classically you take your space-time and you slice it, space like hypersurfaces, and you assume that, well, the slicing is arbitrary, And for that reason, when you do the quantization, you find that the wave functional no longer depends on t.
Yes, yes.
Now, you know, there's no, I mean, in de Broglie-Bohm theory, well, I will still have, you know, the three geometry evolving in time. So, I mean, psi is still time independent, but a general probability distribution, the reason it's time dependent is simply because, well, the trajectories are time dependent. So for a general distribution, in general, P will also be time dependent. There are some issues. I mean, I'm not sure if you actually, maybe, I guess maybe you're thinking of this. It is related to what you're saying. I did mention at one point when I wrote down the equations for the full quantum gravity theory that there are some issues which I think are not fully understood about the theory that involves precisely this question of the arbitrariness of the slicing. Some of the papers, for instance, the paper by Shtanov that I quoted in 1996, he claims that that this arbitrariness of the slicing is broken because of the non-locality, and that maybe this is an issue because there's not obvious, well, how do I have to pick a preferred slicing or what? And a few people in the literature have touched on this. I think nobody seems quite sure what to make of it, but there is a paper by Pinto-Neto and Santini in 2002, which was published in General Relativity and Gravitation, which for some reason is not cited very much, but I think is maybe very significant. Is what they do is they look at the what's called the consistency of the initial value problem. So classically, in classical general relativity, if I write general relativity in Hamiltonian form, so I put initial conditions on a hypersurface and I evolve, I get a space-time. It had better be that if I start with a different hypersurface and evolve, I should get the same space-time. And this is something that was studied, I think in the 70s, there are papers by Teitelbaum and various other people, showing that if these things that appear in the formalism called the constraints, the Hamiltonian momentum constraints, if they satisfy a certain algebra, then you get consistency. The space-time that you get doesn't depend on the slicing. And of course, the constraints that you get from classical general relativity do satisfy that algebra. So it all works. What Pinto-Neto and Santini do is they do an analogous analysis for de Broglie-Bohm pilot wave theory, which you can write in a Hamiltonian form, but where the dynamics is modified by what's called the quantum potential. Now, what they do is quite intriguing. They find that the algebra of the constraints does close, and it's a bit like what's called the Dirac-Teitelbaum algebra, but is modified by the quantum potential. Now, the way they interpret the results is that they claim that the dynamics is consistent. Doesn't matter what slicing you choose, you will get the same space-time. However, the space-time is not Lorentzian. Okay, there's no, it's not a locally Lorentzian space-time. Now, I find this paper very interesting. I've discussed it with Nelson. I'm not sure I fully understand the physics of this. I mean, because it seems to me to be saying that in de Broglie-Bohm pilot wave theory, somehow in the full theory, of course, in these mini superspace models, you've just picked a slicing, so the thing doesn't come up. But in the full theory, which of course is very hard to work with, it looks as if what must be happening is that if you're given a wave functional and you're given a 3 geometry, that somehow the embedding of that 3 geometry in space-time is fixed by the theory. In effect, there's a sort of effective preferred slicing. Now, I have an intuitive argument for why this sort of makes sense. If you think of conventional pilot wave theory, say for a particle, if you're given a wave function and you're given the position, the momentum is automatically fixed. It's not a free parameter, it's fixed, okay? The analog of that in quantum gravity is that, well, if I'm given a Wheeler-DeWitt wave function, I'm given the 3 geometry, the canonical momentum is fixed. Now, the canonical momentum is basically proportional to the what's called the extrinsic curvature of the 3 geometry, which basically tells you how the 3 geometry is embedded in space-time. So it looks as if somehow the slicing is going to be fixed by the wave function of the 3 geometry, which, to be honest, to me, it sounds like an extraordinary claim. I think if it's true, then it's a remarkable property of de Broglie quantum gravity. Now, I'm not entirely sure that it's true. I'm not sure I understand this. So there is this issue. I mean, in this talk, in this paper, I focused on, probabilities in this theory. This issue of the slicing and how that fits with the non-locality of the theory, I think there are things that are still need to be understood. But I think a good starting point is this paper by Pinto-Neto and Santini in 2002.
Okay.
Sorry, again, another very long rambling answer, but there we are.
You motivate me to read more about that.
There is a finger from Karl Hofer on the first question.
Hello.
Hi, Antony.
Hello there. Hello, how are you?
Good. Yeah, I had something very similar to Aurelian's first question.
Yes.
And I liked your answer. It gives me something to think about, to dig into. But it also made me wonder whether there's a problem lurking here for the Bohmians who want to have a perspective on which there's just one universe, one geometry, and so on, versus those who might just be more attracted to a stochastic underlying picture. And so the question is whether this whole framework which you laid out would be adaptable to something that's more like a stochastic theory, perhaps a theory in which different bits of space always have an intrinsic geometry and they're evolving over time, but there's a stochasticity to it. It's not a deterministic evolution.
So, I mean, there are, sorry, are you thinking of something like, sort of Nelsonian mechanics, that kind of thing? There are what you might call stochastic analogs of the de Broglie theory. I don't think, I mean, you could, I'm sure you could write down something comparable for quantum gravity. I mean, to be honest, I've never found these stochastic theories particularly interesting. I mean, I'm sort of interested by determinism, by the idea that underlying quantum probabilities, there is something deterministic, and that there's just a sort of apparent stochasticity because we're stuck in this equilibrium state. I suppose perhaps what you're suggesting is that if maybe there would be an advantage if the theory was stochastic, that there might be less issues concerning the slicing and non-locality. Is that what you're suggesting?
I don't, not so much that.
I mean, I haven't really thought about this.
I'm just worried about the general underdetermination of this kind of approach compared to others.
Underdetermination. So what do you mean?
By the evidence.
Sorry?
Underdetermination by the evidence, because what you'd like is to eventually be able to get some observational evidence that.
Oh, I see. Right. Okay. So you're talking about the fact that when you're in equilibrium, much of the underlying physics is hidden, and then there are issues of falsifiability, and which I agree with. I mean, this is I think an important point. There are there are some people who supporters of de Broglie. There's this in particular. There's this what I call the Bohmian mechanics school of de Broglie theories of Dur, Goldstein, Zangi. They tend to think of the Born rule as built into the theory, and that they have arguments about typicality and so on, which I think are very misleading. And I have published an extensive critique of this a couple of years ago. And one point there is that, well, I mean, let me put it this way. Their view tends to be that, look, the equilibrium theory is the theory, and there's nothing wrong with that. I mean, I think there is something wrong with that, and I think most scientists and probably perhaps a lot of philosophers would think, well, hang on, what you're saying is you've got this theory in which you've got these underlying trajectories that do all these amazing things, but in principle, it's most of the details are forever unobservable because basically it gets washed out by this chi-squared background noise, if you like. Is that, you know, logically, of course, it's a possible, the universe could just be like that. You know, logically it's possible, mathematically it's possible. I think scientifically it doesn't sound right. It doesn't sound right. You think if this is true, if there really is this underlying structure, there's this non-locality, these trajectories, all these amazing things that are happening. Now we can't see it. There must be a way to see it somehow. And you know, so I think there must be some correction somewhere, whether it's from quantum gravity, whether it's from, you know, something I've worked on a lot, looking for some sort of residual non-equilibrium from the early universe. There must be a way through, you know, out of this. You know, if you tell, what I'm saying is, if you take this theory seriously, I think you have to be looking for some kind of deviations from equilibrium and some sort of empirical window, as it were, into this structure. Otherwise, I agree with you. Then you've got this problem where you've got this structure. For instance, I could define a different set of trajectories that preserve psi squared as well. How do I know what's the true velocity field? If you're telling me I'm never ever going to know in principle, well, I think scientifically, then there's something wrong there.
Thanks.
Pleasure. Thank you.
There's a finger from Carlo.
Hello, I've been waiting for you.
Are we in time? I mean, are we late? It's because
you can go. Don't worry.
Oh, it's just a very short thing, Anthony. This is again about the distribution. You gave a long the sort of the fluctuations in cosmologies versus the distribution of many universes. You gave a long answer. I do understand that if you want to fix the details, it requires some details. But isn't your answer essentially just a standard relation between sort of a Boltzmannian and a Gibbsian view of distributions? When you, I mean, if you describe a gas in a room, you can say, given a molecule chosen randomly, there is a distribution in its velocity, or you can take a Gibbs perspective in which you have many copies of the same gas. Aren't you just rerunning that argument? Is it with more details for the universe? When you were sort of...
I hadn't thought of it that way. I mean, what the sort of answer that I gave, I was basically kind of trying to sketch what cosmologists do when they're studying the cosmic microwave background. I mean, as I said, if you look at the papers and the books, often there's a little jump in the steps, and it's not quite, or at least it wasn't clear to me exactly what they were doing, but I think I figured it out eventually. And you know, and the similar thing is done when people look at distributions of galaxies. You know, what you're essentially assuming is that the distribution that we see is a realization from some underlying theoretical.
No, I understand. I don't want you to rerun the same argument. I'm just asking whether you thought there was a connection, but you say you're not.
Maybe there is. Maybe there is, but I hadn't really thought of it that way.
Thank you.
Okay.
Okay, thank you. If there is no other question, we can have a small one if there is. Otherwise, we can have a 8-minute break. So we reconvene at 10 minutes to 4 European time in 8 minutes. See you later. Thank you again, Anthony.
All right, thank you.
So